Welcome to The Explainer. Today, we're going on an absolutely wild journey. We're going to start way down in the microscopic physics of computer processors, and then we're going to zoom all the way out to high-stakes DeFi architecture on Arbitrum. We're exploring a totally fascinating story about what happens when pristine academic whiteboard math collides head-on with the unforgiving physical realities of bare-metal computer hardware.
So let's jump right into this with a really high-stakes question. How exactly did a brilliant mathematical breakthrough accidentally invite a chaotic gambler into a multi-million-dollar vault? I mean, we intuitively feel like computers just kinda get us, right? You click a button and boom, something happens. But there is actually a massive, gaping chasm between our abstract intent in the cloud and the actual physical machines executing the code. And today, we're gonna see exactly how trying to bridge that gap nearly broke a highly advanced financial protocol.
Section 1. The Polar Coordinate Dream.
Okay, to really understand the trap here, we first have to understand the vision. Historically, automated market makers, or AMMs, have basically forced liquidity into simple, isolated pairs of tokens, sitting on standard, clunky Cartesian grids. But OrbSwap, they wanted to build something way more capital efficient. They envisioned this n-dimensional AMM designed specifically for stablecoins. The goal was to allow liquidity provision across dozens of assets simultaneously, all grouped into one unified pool. But to pull that off, they literally had to escape the limits of traditional X and Y axis. Instead, they aimed for a system where all these assets dynamically orbit a $1 peg.
And when you compare the two approaches side by side, you instantly see why you'd want to escape those Cartesian limits. Traditional Riemann integration is, well, it's incredibly blocky. When you try to capture a smooth curve using those rectangular grids, you're basically just guessing at the true body of the data, and that leaves a huge margin of error on the table. But contrast that with polar tick integration. By shifting over to polar coordinates and utilizing angles, the tracking of liquidity becomes flawlessly smooth and highly granular. It captures heavy-tailed distributions perfectly. On paper, it is a total night and day difference.
Section 2. The Trigonometric Catch. So the theory here is a seamless geometric dream. But, and this is a big but, there is a massive technical wall they had to climb. OrbSwap engineers designed what's called a super ellipse invariant, effectively treating the liquidity pool as a circular manifold. Think of a stablecoin pool where everything is perfectly priced at $1. In that scenario, the neutral polar tick sits exactly at a 45-degree angle. Any price movement at all is simply measured as an angular deviation away from that center. So converting one token to another isn't some algebraic headache anymore, it's just treated as rotating an angle. Sounds great, right? Well, rotating along a circle requires serious trigonometry. You fundamentally need complex sines, cosines, and square roots just to make these basic trades work.
And here is where the problem really starts. Standard computer chips, they don't naturally speak trigonometry. To execute these continuous infinite decimal calculations at blistering speeds, they rely on hardware shortcuts. As Kyle McLean-Smith perfectly sums it up in our source material, it's fundamentally an approximation system, not real arithmetic. And that right there introduces a massive hidden flaw in modern computing architecture.
Section 3. The FPU Gambler versus the ALU Surveyor.
To really grasp what Kyle means, we need to shrink all the way down to the microscopic silicon level. Inside your computer chip right now, there's basically a turf war over how math is done. On one side, you have the floating point unit, or what we can call the FPU Gambler. It's incredibly fast, but it's lossy and it's probabilistic. It's essentially frantically throwing darts at a board to guess complex math. To achieve that crazy speed, chip manufacturers literally burn completely secret proprietary seed tables directly into the physical silicon. On the exact opposite side, we have the arithmetic logic unit, the ALU Surveyor. This guy deals in undeniable discrete mathematical truth. Its logic gates execute with 100% deterministic precision. 1 + 1 is 2 every single time.
Now, because the FPU Gambler relies on those hidden corporate trade secret tables, calculating something like the square root of 2 on an Intel chip might actually give you a fractionally different decimal result than the exact same calculation on an ARM chip. Researchers call this phenomenon non-deterministic drift. Simply put, getting exact one-to-one mathematical reproducibility across different machines using floating point math is physically and mathematically impossible.
And relying on this FPU Gambler creates a devastating real-world consequence that we can call the wood chipper effect. Once your exact source data is ingested, the hardware constantly chops off tiny fractions, like, say, the 23rd decimal bit, just so it can squeeze continuous numbers into fixed memory slots. When that happens, the original data provenance is completely and permanently destroyed. Think of it like a giant digital blender. You might know exactly what fruits you tossed in initially, but once it goes through those FPU approximations, there is absolutely no way you can unblend that smoothie back into its original ingredients. The chain of mathematical truth is just obliterated.
Section 4, the determinism mandate. Now look, if you're just browsing the web or playing a game, a microscopic rounding difference doesn't really matter. But in decentralized finance, it is a completely different story. When we try to force this lossy hardware reality into a crypto network, we crash into multiple variance vectors. Maybe it's the physical microarchitecture of different CPUs implementing rounding slightly differently. Maybe it's compiler optimizations, reordering math operations under the hood. Or maybe it's just the non-associative nature of rounding to fit fixed mantises. Whatever the vector, the result is the same. No two machines are guaranteed to agree on the exact same floating point calculation.
So what does this all mean for a blockchain? It's a total disaster, because blockchain consensus requires absolute, bit-perfect agreement across thousands of totally heterogeneous nodes. Determinism isn't just a nice-to-have, it's absolute law. If an Arbitrum smart contract uses the FPU Gambler, node A running an AMD chip might calculate a fractional token balance differently than node B running an Intel chip, and that instantly violently shatters the cryptographic consensus. The network literally cannot agree on universal truth, triggering a catastrophic fork where the entire financial ledger just splits in two.
Section 5, the floating point trap.
Which brings us right back to the smoking gun in OrbSwap's design. The pristine academic theory of polar coordinates is beautiful on a whiteboard, but the researchers left a massive, glaring blind spot when it came time to translate that theory into code. The official OrbSwap research paper and the referenced Rust implementation explicitly utilized F64, which stands for 64-bit floating point variables, to compute the sines and cosines for their swap functions. By writing their smart contract code this way, they were actively, voluntarily inviting the chaotic FPU gambler to manage a multi-million-dollar vault. Now, you might be wondering, is a tiny rounding error really that big of a deal? And sure, during calm, sideways trading days, you might never notice it. But what happens during an extreme stress test? Think back to the Silicon Valley bank collapse and the absolutely crazy stablecoin run we saw in March 2023. A massive panic event triggers violent liquidity shifts across these n-dimensional pools. When you start violently pushing extreme numbers through high-dimensional floating point math, those microscopic errors don't just sit there. They compound wildly. The trigonometric angles stretch out, the hardware approximations widen, and the risk of catastrophic precision loss absolutely skyrockets. Building on this foundation is literally like waiting for a market earthquake to bring the entire protocol down.
But wait, here is the massive plot twist of the whole story. The blockchain environment that OrbSwap was actually building for, Arbitrum Stylus, has a built-in defense mechanism. Arbitrum enforces a strict validation whitelist that automatically, immediately blocks all native WebAssembly floating point instructions. If the compiler detects native floating point instructions during the contract activation phase, it completely fails with a validation error. The network actively prevents developers from deploying the FPU Gambler on-chain just to save the ledger from non-determinism. No floating points allowed. Period.
So suddenly, the developers are faced with a massive dilemma. Their pristine theory desperately requires continuous floating point math to pull off these beautiful trigonometric rotations, but the concrete reality of the blockchain explicitly bans it. So to deploy on-chain, developers are forced to become digital archaeologists. They have to ditch the native floats entirely and painstakingly translate the whole polar framework into strict, fixed-point integer math. They end up relying on soft floats, software emulation, and heavy libraries like PRB math, artificially scaling values by 10 to the 18th power, known as WAD scaling, just to mimic decimals using whole numbers.
And let's be totally real about what this workaround actually costs, because it is not cheap. Emulating true sines and cosines using scaled integers requires implementing incredibly complex approximation algorithms like Taylor series or Cordic routines. These emulated pipelines require dozens, sometimes hundreds of integer instructions per step just to manually shift bits and handle mantissa rounding so they can bypass the physical FPU entirely. This causes severe gas spikes and massive computational overhead. It completely erodes the execution efficiency of the WebAssembly virtual machine. The mathematical elegance of polar coordinates comes with a devastatingly high gas cost when forced to run as integers. In fact, research from our sources shows that relying on native, discrete integer geometric rigor instead of these emulated approximations yields a staggering 74 times reduction in metabolic energy. It is frankly mind-blowing just how much overhead this emulation demands.
So, as we wrap up today's explainer, I really want to leave you with a provocative thought to chew on. Bridging the gap between a pristine whiteboard theory and the strict deterministic reality of physical silicon is without a doubt one of the hardest engineering challenges in decentralized finance today. As we continue to build out the future of high-stakes decentralized computing, are you willing to settle for a microchip's best guess, or will you demand perfect mathematical truth? Thanks so much for joining me to explore this incredible architecture. Keep questioning the systems you rely on every day, and I'll catch you in the next explainer.